There is a photograph that took a telescope 1,000,000 miles from Earth, almost 2 full weeks to gather. If you held up a single grain of sand at the end of your outstretched arm, it would cover the exact patch of sky this image came from. A piece of darkness so small it looks like nothing at all. And inside that nothing, when the light finally arrived, there were thousands of galaxies. We built a machine to look back almost to the beginning. We carried it past the moon, unfolded it in the cold, and pointed it at the emptiest corner of the night we could find. We expected the early universe to be faint and shapeless and slow to assemble. That is the story we had told ourselves for 100 years. The light came back wrong. The galaxies were already there, too soon, too bright, too settled, as if the universe had skipped the first chapters of its own story. There were small red points of light no one could quite explain, and there was a single number, measured 2 different ways, that refused to agree with itself. A quiet contradiction sitting at the center of everything we thought we knew. Tonight, we are going to travel out to the edge of what any instrument has ever seen, and then a little further, into the place where our best maps simply stop. We are going to look at what the James Webb Space Telescope actually found out there. Not to be frightened by it, to be amazed by it, and to feel, by the end, a little more at home inside something this large and this old and this strange. Let your breathing slow. There is no hurry out here. Light has been traveling toward this moment for 13 billion years, and it can wait for you to get comfortable. The telescope is called the James Webb Space Telescope, and it does not orbit the Earth the way you might imagine. It sits 1.5 million kilometers away from us, at a balance point in space where the pull of the Earth and the pull of the Sun hold steady against each other, so that a single golden mirror can float there in near-perfect stillness and stare into the dark without our planet ever getting in the way. It launched on Christmas morning in 2021, folded up like a piece of origami inside a rocket, because the mirror was too wide to fly any other way. For the first month of its life, it did nothing but travel and unfold. 344 separate steps that each had to work perfectly, with no one able to reach it if anything went wrong. By the summer of 2022, it had opened its eye, and the first images came home, and the people who had spent 30 years of their lives building it sat in a quiet room and wept. What makes it different from every telescope before it is the kind of light it was built to catch. The universe is expanding, and that expansion stretches the light traveling across it, pulling the color of ancient starlight out of the visible range and down into the infrared, the warm, slow light you feel rather than see. The oldest galaxies are not blue or white to us. They are deep red, red-shifted by the long journey, and Webb was designed from the beginning to read exactly that faded, stretched, infrared whisper. To do it, the instrument has to be colder than almost anything else in the solar system. A vast silver sun shield, the size of a tennis court, keeps the sun's heat off the mirror, holding the cold side near -230 degrees, because warmth itself glows in the infrared and would drown out the faint old light it came to find. It is, in a sense, a machine built to be quiet enough to hear the softest signal in the universe. The eye itself is a marvel worth pausing on. The mirror that gathers the light is not a single sheet of glass, but 18 separate hexagonal segments, fitted together into one golden surface more than 6 meters wide. Each segment carved from a light and stable metal called beryllium, and then coated in a microscopically thin layer of real gold. Gold, because gold reflects infrared light better than almost anything else we know, and infrared was the whole point. The segments can be nudged individually, by motors finer than the eye can follow, until all 18 behave as a single, perfect mirror. We polished metal to the smoothness of a still pond and gilded it, and sent it out into the cold so that it might catch light older than the Earth. And the first deep image it released showed us a patch of sky in the southern constellation of Volans, a region called SMACS 0723. In the foreground sat a cluster of galaxies so massive that its gravity bent space itself, acting as a natural lens, magnifying and smearing the light of even more distant galaxies sitting far behind it. We were looking through one part of the universe to see another, using the warp of space-time as a magnifying glass we did not build and could never have built. There is a strange tenderness in that idea if you sit with it.
The light in that picture left its galaxies before the Earth existed, before the sun had formed, before there was an ocean or a single living cell anywhere that we know of. It crossed the widening dark for billions of years, and it happened to arrive at the one brief moment when a species had finally made something patient enough and cold enough to catch it. A few million years earlier or later, and there would have been no one here to look. The deeper Webb looked, the further back in time it saw, because light is slow and the universe is wide. And to look out across space is always to look backward into the past. The faintest specks in its images are not nearby. They are the most distant objects ever recorded. Galaxies as they were when the cosmos was only a few % of its present age. Their light, a kind of fossil, a message sent from a beginning we can no longer visit any other way. We had a theory about what that beginning should look like. We thought the first galaxies would be small, ragged, dim, still gathering themselves out of the darkness, taking their time to grow into the grand spirals and ellipses we see around us now. We had equations for it and simulations, and a confidence built up over decades. And then the machine sent home what was actually there, and the careful story we had written began, very gently, to come apart. In the first year of Webb's observations, a team led by the astronomer Ivo Labbé published a paper describing 6 galaxies that, by every expectation we had, should not have existed. They sat at enormous distances, their light dating from only 500 to 700 million years after the Big Bang. And yet, they appeared to hold as many stars as the fully grown Milky Way holds today. Entire mature galaxies, somehow already assembled when the universe was still in its infancy. The press called them universe breakers, which is a dramatic phrase for what was really a very precise kind of surprise. Nothing about them broke the laws of physics. What they strained was our timeline, our sense of how long it should take for gravity to gather ordinary gas into stars, and stars into the vast organized swarms we call galaxies. They seem to have done in a few 100 million years what we thought required billions. Some of those first measurements were later softened. Galaxies are hard to weigh from billions of light years away, and part of the red glow that looked like the light of countless stars turned out, in some cases, to come from something else hiding at their centers. The number of true, impossible galaxies shrank as the data improved, the way early surprises often do. But it did not shrink to zero, and that is the part worth holding on to. Because even after the corrections, the early universe that Webb revealed was brighter and more crowded than our models had predicted. Galaxy after galaxy appeared too luminous for its age, lit up far more than the slow, patient assembly of stars could easily explain. Something in those first few 100 million years was building light faster, or more efficiently, or by some route we had not thought to include in our equations. The most distant of all of them carries the plain catalog name JADES GS Z140, found in a deep survey region that Webb has returned to again and again. Its light left it around 290 million years after the Big Bang, which means that when this galaxy shone, the universe had completed barely 2% of the time it has lived so far. And yet, it is not a faint smudge. It is large and luminous, and already full of the heavier elements that only generations of stars can forge. For a sense of how far that record has moved, consider that for years, the most distant known galaxy was one called GNZ11, first spotted by the older Hubble telescope, its light dating from about 400 million years after the beginning. That object had seemed to sit almost at the boundary of the visible. Webb did not merely match it. It reached past it, again and again, until the old frontier became just another landmark on the way out. And there is a crucial difference between guessing a galaxy's distance and knowing it. The first estimates of these record breakers came from the colors of their light alone, a method that can sometimes be fooled. To be certain, astronomers spread the light into a full spectrum and search for specific fingerprints that pin the distance down beyond argument. When they did this for the most distant candidates, the great distances held. These were not nearby galaxies wearing a disguise of red. They were genuinely there, at the dawn, exactly as far away as they had seemed.
There is a galaxy in these surveys that the astronomer Stephen Finkelstein named after his young daughter, Maisie's galaxy. Its light, dating from around 400 million years after the Big Bang, discovered in a region called CEERS that Webb mapped in its first months. There is something quietly human in that gesture, in carrying a child's name to the oldest light we have ever confirmed, as if to say that the deep past and the small present belong to the same family after all. As the surveys grew, so did the strangeness. One of the largest programs Webb has undertaken, an ambitious mapping of a wide patch of sky, set out to chart hundreds of thousands of galaxies across cosmic time. And in its early data, it kept finding the same thing the smaller surveys had only hinted at: bright, well-formed galaxies appearing earlier and in greater numbers than the models comfortably allowed. It was never one anomalous galaxy that troubled the theorists. It was the steady accumulation of them, survey after survey, each adding another handful of objects that had assembled themselves far too soon. What all of these objects share is a kind of impatience that we did not expect the young universe to have. We had imagined the cosmic dawn as a long, slow gray morning. Webb showed us something more like a sudden sunrise, the lights of structure coming on far earlier and far more brightly than the script allowed. And when the data does that, when reality runs ahead of the theory, scientists do not panic. They get curious. They begin asking what the model was missing. One possibility is that the very first stars were unlike any star alive today, enormous, made of nothing but hydrogen and helium, burning fierce and fast and bright, lighting up their galaxies far more intensely than the gentler stars that came later. Another is that those early galaxies turned their gas into stars with an efficiency that no nearby galaxy can match, wasting almost nothing. And a third possibility
the one that makes cosmologists lower their voices, is that the timeline itself is off, that the universe is not quite the age we think, or did not expand quite the way we assumed in those first uncertain moments. None of these answers is settled, and that uncertainty is not a failure. It is the sound of a field that has just been handed better evidence than it has ever had, and is still learning how to read it. The galaxies that should not be there are still there, every night in the data, patient, red, and very old, waiting for us to understand them. And they are only the first of the puzzles Webb carried home. Scattered through Webb's deepest images, once people knew to look for them, was a population of objects that had never clearly been seen before. Tiny, compact points of light, far too small to resolve into any shape, and a deep, saturated red, unlike almost anything around them. Astronomers, who are not always poets, gave them the plain and oddly gentle name they still carry today: the little red dots. At first they seemed like a curiosity, a handful of strange specks. But as more of the sky was surveyed, the dots turned up everywhere, in their hundreds, concentrated in the first billion or so years of cosmic history. They were not rare accidents. They were a whole class of object, common in the early universe, and almost entirely absent from the universe around us now. A population that flourished at the dawn and then, somehow, faded from the record. When Webb spread their light into a spectrum, the puzzle deepened. The dots showed the signatures of gas moving extraordinarily fast, swirling at speeds that only one thing in nature tends to produce: matter falling toward a black hole. The little red dots, it seemed, were not simply small galaxies. Many of them appeared to be lit from within by a feeding black hole, a bright and violent engine wrapped in so much dust that only the reddest light could escape. That alone would not be strange. Most large galaxies, including our own, hold a giant black hole at the center. What unsettled people was the proportion. In the nearby universe, a galaxy's central black hole tends to weigh a tiny, fixed fraction of all the stars around it, a relationship so steady it almost looks like a law. In the little red dots, the black holes seemed far too heavy for their surroundings, as if the engine had arrived before the rest of the galaxy was built around it. This connects to one of the oldest quiet shocks in modern astronomy, which is the simple existence of giant black holes in the early universe at all. Even before Webb, astronomers had found blazing quasars, black holes already a billion times the mass of the Sun, shining from the first 800 million years of time.
One of them, catalogued as J0313-1806, holds something like 1.5 billion solar masses, and its light dates from a time when the universe should barely have had the time to make it. What makes the dots so hard to settle is that their light seems to tell two stories at once. Spread into a spectrum, it shows a peculiar shape, blue in one part and steeply red in another, as though two different kinds of source had been blended together. Some read that shape as the unmistakable mark of a black hole shrouded in dust. Others see it as the glow of an extraordinarily dense knot of stars, packed so tightly that no black hole need be invoked at all. The same faint smudge supports both readings, and until sharper data can separate them, the little red dots remain genuinely undecided, a kind of ink blot painted in the first billion years. The trouble is that black holes grow by eating, and eating has a speed limit. As matter falls in, it heats and blazes, and that radiation pushes outward against the very gas trying to fall in, throttling the meal. There is a natural rate
beyond which a black hole cannot easily feed. And at that rate, starting from an ordinary stellar seed, you simply cannot build a billion solar mass giant in the time the early universe allows. And yet, there they are. So the little red dots may be a missing chapter in that story. Black holes caught in the act of growing impossibly fast, in the very era when the giants must have been assembled. Or they may be something else entirely, some combination of dense young stars and dust that only mimics the signature of a black hole. The honest answer, as of the most recent surveys, is that we are still arguing about it, and the dots are still there in the data, red and silent, refusing to fully explain themselves. What I find moving about them is how easily we might have missed them. They are faint and featureless, and they look at first glance like flaws in the image. It took a telescope cold and patient enough, and people willing to take a smear of red light seriously, to notice that the early universe was quietly full of these small, burning things. The cosmos does not announce its mysteries. It leaves them lying in plain sight, dim and unremarkable, waiting for someone to look closely enough to be surprised. And each of these puzzles, the galaxies grown too soon, the black holes grown too large, the red dots that should not be so common, points in the same loose direction. The early universe was more active, more luminous, more advanced than the careful models said it had any right to be. Something about those first few 100 million years is running faster than our equations. To find out what, we have to turn from the things we can see directly to a stranger kind of evidence. A single measurement, taken two different ways, that has been quietly disagreeing with itself for years. Almost a century ago, the astronomer Edwin Hubble noticed something that should have been impossible to believe. The galaxies around us are not sitting still. Nearly all of them are moving away from us, and the farther away a galaxy is, the faster it recedes, as if the whole of space were quietly swelling, carrying everything apart from everything else. That relationship between distance and speed is described by a single number, and we still call it the Hubble constant in his memory. That number is, in a sense, the heartbeat of the universe. How fast space itself is expanding right now. And measuring it has become one of the great, careful obsessions of modern science. Because if you know how fast the universe is growing today, and how it has grown in the past, you can read both its age and a great deal of its future. For decades, getting that number was simply hard. In the last few years, it has become something stranger than hard. It has become contradictory. There are two honest ways to measure the expansion, and they no longer give the same answer. The first way looks deep into the past. The faint glow left over from the early universe carries within it a precise pattern, a kind of sound frozen into the infant cosmos. And from that pattern, the rate of expansion can be calculated and projected forward. The Planck spacecraft, which mapped that ancient glow with exquisite care, gives a value of about 67 kilometers per second for every megaparsec of distance. The second way starts close to home and builds outward, rung by rung, along what astronomers call the cosmic distance ladder. It begins with a particular kind of star, a Cepheid variable, which pulses brighter and dimmer in a rhythm tied exactly to its true brightness, a relationship discovered by Henrietta Leavitt more than 100 years ago.
By comparing how bright these stars truly are to how bright they appear, you can measure real distances across space, and then use them to calibrate the brilliant exploding stars that can be seen much farther still. When the team, led by Adam Rees, walked carefully up that ladder, measuring the nearby universe directly, rather than inferring it from the ancient glow, they arrived at a value of about 73. 67 from the early universe, 73 from the late one. The two numbers are close enough to sound almost the same, and far enough apart that, given how precisely each is now measured, they cannot both be simply correct. The universe appears to be expanding faster today than the physics of its youth says it should. The gap is roughly 9%, and what makes it a genuine puzzle rather than a rounding error is how confident each side has become. The chance that this disagreement is a statistical fluke has fallen below 1 in a million. In the language of physics, the two measurements now differ by about 5 standard deviations, the same threshold scientists use to declare that they have discovered something real. We have crossed that line. The disagreement is real. We simply do not yet know what it is telling us. For a long time, the comfortable assumption was that the error must hide in the nearby measurement, that the Cepheid stars were somehow being miscounted, their light blurred together with their neighbors, throwing the whole ladder off. It was the kind of explanation everyone secretly hoped for, because it would have let the standard picture stand. And so, when Webb arrived, with its sharper infrared vision, one of the quiet tests it was asked to perform was to look again at those same pulsing stars and see whether the old measurements had been fooled. They had not. Webb resolved the Cepheids more cleanly than any telescope before it, separated them from the crowd of stars around them, and measured their distances again. The local value held. 73 did not move toward 67. If anything, the tension grew firmer, because the easiest way out had just been closed. There is even a third way to take the measurement, a quieter referee standing between the two rivals. Instead of pulsing Cepheid stars, it uses the steady brightness of the oldest red giant stars at a particular stage of their lives, a method long championed by the astronomer Wendy Friedman. Its answer tends to fall somewhere between the other two, close enough to neither to declare a winner. So the disagreement is not a simple clash of two numbers that one careful measurement could settle. It is a genuine puzzle, with several honest answers clustered around it, and no one yet able to say which is true. The disagreement was not a mistake in the ladder. It seems to be a feature of the universe. And so cosmologists are left holding a small, stubborn contradiction at the very center of their science. A number that means one thing when read from the dawn of time, and another thing when read from the world outside the window. It may mean that something happened in the early universe that we have left out of the equations, some extra ingredient that briefly changed how fast space grew. It may mean that the force driving the expansion is not as constant as we assumed. Or it may be the first clear sign that the model itself, the framework we have trusted for a generation, is incomplete in some deep and not yet visible way. There is no fear in this for the people who study it, and there should be none for you. A contradiction like this is the most precious thing a science can have. It is an open door. It is the universe telling us, gently but unmistakably, that there is more here than we have understood, and pointing us toward the place we have not yet looked. To begin to follow it, we have to go back to that ancient glow itself, the oldest light there is, and read the messages written across the whole sky in the first moments after the beginning. For the first few 100,000 years of its existence, the universe was not transparent. It was a dense, blazing fog,
so hot that atoms could not hold together, every electron torn free and roaming loose. And light could not travel any distance at all before colliding with one of them and scattering away. If you had somehow been there, you would have seen nothing but a featureless glare in every direction, like being inside a star with no surface and no edge. Then, about 380,000 years after the beginning, the universe cooled just enough. The roaming electrons slowed and were captured and settled into orbit around the waiting nuclei. And for the first time, matter became the calm, neutral atoms we know, mostly hydrogen, some helium, the simplest things there are. And in that moment, the fog lifted. Suddenly, light could fly free, across distances that had never been open to it before. The universe became clear. That first freed light has been traveling ever since. For nearly 14 billion years, it has streamed across the widening dark. And the same expansion that stretches the light of distant galaxies has stretched this light too, far more, pulling it down from a blazing glow into the faintest possible warmth. It is still arriving, from every direction at once, falling on the Earth this very second. We call it the cosmic microwave background, and it is the oldest light there is, the farthest back any eye or instrument can ever see. It was found, fittingly, by accident. In 1965, two radio engineers named Arno Penzias and Robert Wilson were trying to remove a faint hiss from their antenna in New Jersey, a persistent noise they could not get rid of no matter where they pointed it. They cleaned the equipment. They evicted a pair of pigeons that had nested inside and scrubbed away what the birds had left behind. The hiss remained, the same in every direction, day and night. It was not interference. It was the glow of the beginning, and they had stumbled into the most important discovery of 20th century cosmology while trying to fix what they thought was a broken instrument. The temperature of that glow today is just 2 7/10 degrees above absolute zero, the coldest temperature there can be. The fire of the early universe has been cooling for 14 billion years, and what reaches us now is barely a whisper above perfect cold, a warmth so faint it took decades to measure properly. The blaze that once filled all of space has become the gentlest hum in the night, and we are bathed in it constantly, unable to feel it, carrying it with us everywhere we go. In 1989, a satellite called COBE was sent up to map that glow with real precision, and what it found was almost unbelievably smooth. The temperature of the ancient light was the same in every direction to within 0.01%, the most perfect uniformity ever measured in nature. A black-body glow so clean that when the physicist John Mather presented the data to a room of scientists, they rose and applauded a graph. The early universe, whatever else it was, had been astonishingly even, the same everywhere, with almost no feature to distinguish one patch from another. But almost is the crucial word, because COBE also found, faintly, the first hint of texture. Tiny variations in the temperature, a few parts in 100,000, spots very slightly warmer or cooler than their surroundings. Those whispers of difference were not flaws. They were the seeds of everything. The slightly denser regions had slightly stronger gravity, and over billions of years, they pulled in more and more matter, growing into the first stars, the first galaxies, the great cosmic structures, and eventually, the world beneath your feet. Every galaxy in the night sky began as one of those faint ripples in the oldest light. Later missions sharpened the picture. A spacecraft called WMAP refined the map at the start of this century. And then the Planck Observatory, working through the 2010s, produced the definitive portrait. A full sky image of the universe as it was at 380,000 years old. Every tiny temperature ripple rendered in fine detail. It is, quite literally, the oldest photograph in existence, a baby picture of everything, taken before there were stars or planets or any of the structure we now call home. There is more written into that ancient pattern than temperature alone. Frozen into the early universe was a kind of sound, pressure waves rippling through the hot plasma before it cooled, and when the fog lifted, those waves were locked in place at a particular size, a little under 500 million light-years across. That frozen scale has served ever since as a cosmic measuring stick, a standard ruler astronomers use to gauge distances across the universe and to trace how the expansion has changed over billions of years. From the same faint glow, we learn not only how the universe began, but how old it is, and that its overall shape is flat to within a tiny fraction of a percent. When you look at that map, you are looking at the surface beyond which no light can carry information to us, the wall of the visible past. It is not a wall in space, exactly. It is a wall in time. The moment the fog lifted, glowing at us from all sides, the same distance away in every direction we choose to look. We sit, always, at the center of a sphere of ancient light, and the edge of that sphere is the edge of what we are allowed to see. And here is where the story turns strange again. That ancient map, so smooth and so uniform, was supposed to be the calmest thing in all of cosmology. Featureless, even, reassuringly plain.
But when astronomers studied it closely, down to its faintest patterns, they began to notice a handful of marks that no one has been able to fully explain. The oldest light, it turns out, has a few secrets written into it. And before we go on, I want to ask you something gentle about it. Take a moment, before we look at the strange features, simply to hold the idea of what this map is. It is a picture of the entire universe when it was 380,000 years old, glowing softly from every direction around you, older than every star, older than time as anything alive has ever measured it. If, lying here in the dark, that thought stirs anything in you at all, wonder, smallness, a strange kind of comfort, I'd love for you to leave a single word in the comments for it. Just one word, whatever surfaces. It's a quiet thing to read, later, the words people reach for when they think about the oldest light there is. Now, to the marks themselves. The first and most famous sits in the southern constellation of Eridanus, the river, and it is known simply as the cold spot. It is a region of the ancient sky noticeably colder than the gentle average around it, about 70 millionths of a degree cooler, spread across a patch far wider than such a feature has any easy right to be. In a map that is supposed to be smooth to 1 part in 100,000, the cold spot stands out like a single, deep bruise on otherwise even skin. For years, people have tried to explain it, and the most natural idea is that the cold is not really in the ancient light at all, but acquired along the way. If the light from that direction happened to pass through an enormous, unusually empty region of space, a supervoid, hundreds of millions of light-years across, it would lose a little energy climbing out of that emptiness, arriving to us very slightly cooled. Astronomers have looked, and there does seem to be a large, under-dense region in roughly the right direction, an Eridanus supervoid that might account for at least part of the chill. But the numbers have never quite closed, and that gap has left room for stranger thoughts. There is a speculative idea, taken seriously by only a few but never quite dismissed, that the cold spot could be something far more exotic, a mark left by contact, in the earliest instant, between our universe and another one. We will come, much later tonight, to where an idea like that even comes from. For now, it is enough to know that one of the coldest patches in the oldest light has never been fully explained, and that some careful people have wondered, quietly, whether it is a fingerprint of something outside everything we know. The second oddity is harder to picture, but in some ways more unsettling to the people who study it. The largest temperature patterns across the whole sky, the broadest, gentlest variations, the ones that span half the heavens, appear to line up with one another in a way they have no reason to. And worse, they seem faintly aligned with the plane of our own solar system, as though the grandest features of the infant universe somehow knew about the orbit of the Earth. Two physicists, Kate Land and João Magejo, gave this strange alignment a half-joking name that stuck: the axis of evil. The name is dramatic, but the worry behind it is real and very simple. The early universe should have no special direction. It should look statistically the same whichever way you turn, with no axis, no preferred orientation, no sense of up or down written into it at the largest scales. An alignment like this hints, faintly, that perhaps it does have a direction after all, or, just as likely, that we are being fooled by chance, seeing a pattern in the one and only sky we will ever have to measure. That last possibility deserves its due, because it may well be the answer. We have exactly one universe to observe, one sky, one ancient map. When you only get to roll the dice once, you cannot tell a meaningful pattern from a lucky coincidence the way you could with 1,000 rolls. Cosmologists call this cosmic variance, and it haunts every claim about the largest scales. The cold spot, the axis of evil, a faint lopsidedness between one half of the sky and the other. Each of them might be a genuine clue, or each might be the kind of accident that any single random sky would happen to contain. And that is precisely what makes them so tantalizing. We cannot run the experiment again. We cannot make a second universe and check whether these marks appear in that one too. We are left to study the single example we were given, turning it over and over, trying to tell which of its features are messages and which are merely the texture of one particular roll of the cosmic dice. The honest scientist holds both possibilities at once and is patient and keeps looking. There is a quieter anomaly too, easy to overlook beside the others.
The very largest ripple that should appear across the ancient sky, the broadest swell of warm and cool, comes out fainter than the standard picture predicts, as though the universe were strangely calm at its grandest scale. On its own, it would mean little. Stacked together with the cold mark and the alignment and the faint lopsidedness between the two halves of the sky, it adds to a quiet feeling among some cosmologists that the largest scales of the universe are not quite behaving the way the textbook says they should. What I want you to take from all of this is not suspicion, but a kind of awe at the strangeness of our situation. We have a photograph of the beginning of everything, and even it is not perfectly plain. It has a cold mark no one can fully account for, and an alignment that should not exist, and a faint lopsidedness, all written into light that left its source before the first star was born. Whether those marks are accidents or clues, they tell us the same humbling thing, that the universe at its largest and oldest is still, in real ways, a mystery we have only begun to read. And the mystery does not end with the ancient light. It is written into the shape of everything that came after, in the vast architecture of galaxies that the light's faint ripples slowly grew into. When those faint ripples in the ancient light began to grow, they did not grow evenly. Gravity is patient and relentless, and over billions of years, it gathered matter out of the smoothness into an enormous, delicate architecture. Not a random scatter of galaxies, but a structure, vast and intricate, that we are still mapping today. Astronomers call it the cosmic web, and once you have seen it, the night sky never looks quite the same. The web is built of filaments, long, glowing threads of galaxies stretched across hundreds of millions of light years, meeting at dense knots where clusters of thousands of galaxies gather. Between the threads lie sheets and walls, and between those lie the voids, immense, nearly empty bubbles of darkness, far larger than the lit regions, so that most of the universe by volume is simply nothing at all. If you could pull back far enough to see it whole, the universe would look less like a sky full of stars and more like sea foam, or the branching of nerves, or the inside of a sponge held up to the light. Our own galaxy sits in a quiet corner of this structure, in a small gathering called the local group. The Milky Way, the Great Spiral of Andromeda, and several dozen smaller galaxies bound loosely together by gravity. It is a modest neighborhood by cosmic standards, a handful of lights in an unremarkable part of the web. For most of the 20th century, we assumed that was nearly the whole story of our address. Then, in 2014, a team led by the astronomer Brent Tully traced the motions of the galaxies around us and discovered that our neighborhood belongs to something far larger than anyone had drawn before. They followed the gentle flows, the way thousands of galaxies drift, all of them sliding slowly toward common regions, and used those flows to define the true boundaries of our home supercluster. They named it Laniakea, a Hawaiian word meaning immeasurable heaven, and it stretches some 520 million light-years across and holds the better part of 100,000 galaxies. We do not sit anywhere near its center. The Milky Way lies far out on one of Laniakea's outer fringes, on a thin filament near the edge, and all of it, our galaxy, our whole supercluster, is drifting, caught in a slow current flowing inward toward a single region deep in the structure. There is something out there, a great concentration of mass, and we and everything around us are quietly falling toward it. That region has a name that astronomers gave it before they could even see it clearly: the Great Attractor. It lies in the direction of the southern constellations of Centaurus and Norma, and it pulls our entire supercluster toward it at hundreds of kilometers every second. A motion we did not choose and cannot feel, carrying the Earth and the Sun and all the stars of the Milky Way steadily across the sky toward a destination we may never reach. For a long time, we could not even look at it directly, because it lies hidden behind the worst possible obstacle: our own galaxy. The flat disk of the Milky Way, thick with stars and dust, blocks a wide band of the sky from view, a region astronomers call the zone of avoidance, and the Great Attractor sits squarely behind it. We have had to peer around the edges and through the dust in wavelengths that can pierce it, slowly assembling a picture of the thing that is pulling us, like trying to make out a mountain through fog. What we have found behind that fog is humbling. The Great Attractor is real, a genuine overdensity of galaxies, but it is not even the largest player. Beyond it, further still, lies the Shapley supercluster, the densest concentration of galaxies in our part of the universe, and much of the pull we feel may come from that greater mass lying far behind the nearer one. It helps, sometimes, simply to pause on the number of these islands of light. Careful counts that account for all the faint galaxies too dim to see directly suggest that the observable universe holds something on the order of 2 trillion galaxies, each one a swarm of hundreds of billions of stars. That figure is so far beyond what the mind can hold that it stops being a number and becomes a kind of feeling. Every one of those 2 trillion galaxies is a place with its own long history, its own dying and newborn stars, its own quiet corners where light falls on worlds we will never name. We are being drawn not toward one thing, but toward a hierarchy of things, each larger and farther than the last. And in 2017, a team led by Yehuda Hoffman added the final strange piece. We are not only being pulled, we are also being pushed. They identified a region on the opposite side of the sky that is unusually empty, a great absence of galaxies. And because emptiness exerts a kind of relative push compared to the denser regions around it, this void is helping to drive us along. They called it the dipole repeller, and so our true motion through the universe is the sum of 2 gentle forces, a pull from the densest place we know, and a push from the emptiest. We can even measure our motion against the oldest light itself. Because we are moving through it, one side of the ancient sky appears very slightly warmer, and the opposite side very slightly cooler. A gentle lopsidedness that reveals the sun traveling at something like 370 kilometers every second relative to the glow of the early universe. We are not at rest with respect to the beginning. Nothing is. Everything drifts against everything else, against the ancient light, in a vast and silent motion we never feel. All of this means that the Earth is not still, and never has been. Beneath the spin of the planet, beneath its orbit around the sun, beneath the sun's long circuit around the galaxy, our whole galaxy is sailing through the cosmos at roughly 600 kilometers every second, drawn and driven across the cosmic web toward regions we are only beginning to map. You are moving, right now, faster than you can imagine, carried by the architecture of everything, and it feels, as it always has, exactly like lying perfectly still in the dark. There is an assumption that sits quietly underneath nearly all of modern cosmology, so basic that it is easy to forget it is an assumption at all. It is the idea that the universe, if you stand back far enough, is the same everywhere. That one large region looks statistically like any other, with no special places and no preferred directions. Matter spread evenly when you blur your eyes enough. Cosmologists call it the cosmological principle, and almost everything we calculate depends on it being true. The principle does not claim that the universe is smooth up close. Up close, it is all texture, stars and galaxies and the filaments of the web. The claim is about the largest scales, that above some size, perhaps 1 billion light-years or so, the lumpiness should wash out, and any patch of the cosmos that big should contain roughly the same amount of stuff as any other. Below that size, structure. Above it, sameness. That boundary is what keeps the universe describable by a single set of equations. The trouble is that we keep finding things that are too big. In 2003, a survey of galaxies revealed an enormous wall of them, a sheet stretching well over 1 billion light-years, which became known as the Sloan Great Wall. It sat uncomfortably close to the size where structures are supposed to stop forming, a single coherent feature pushing against the limit of what the principle allows. It was impressive, and it was troubling, and it was only the beginning. In 2013, astronomers studying the brief, brilliant flashes called gamma-ray bursts, the most powerful explosions in the universe, each marking the death of a massive star or the collision of dead ones, noticed that the bursts were not scattered evenly. A great many of them seemed concentrated in one vast region of the sky, suggesting an underlying structure of almost unbelievable extent, something on the order of 10 billion light-years across. They called it the Hercules Corona Borealis Great Wall, and if it is real, it is the largest structure ever identified, so large that light itself would need a sizable fraction of the age of the universe to cross it. A structure 10 billion light-years wide should not exist.
It is many times larger than the limit the cosmological principle sets. Far too big to have assembled in the time available. Far too big to be just another lump in a universe that is supposed to be smooth at that scale. Either our understanding of how structure grows is missing something important, or the gamma-ray bursts are tricking us, their apparent clustering a quirk of incomplete data rather than a true wall of matter. The debate over which it is has not ended. These were not the first hints of trouble either. Years earlier, the astronomer Roger Close had mapped an enormous grouping of quasars, brilliant galactic cores strung across some 4 billion light-years of space, a structure that already strained the rule about how large things are permitted to grow. In the standard picture, the universe should smooth out into sameness once you average over regions only a few 100 million light-years across. Each of these discoveries pushes against that comfortable threshold, and whether they finally break it or merely bend it is one of the genuinely open questions of the field. Then came a young researcher named Alexia Lopez, who found a way to map the unseen by using the light of distant quasars, brilliant beacons whose light, passing through intervening gas on its way to us, picks up the fingerprints of whatever it crosses. By reading those fingerprints across the sky, she traced out structures too faint to see directly. And what she found, announced first in 2021 and then again in 2024, were two of the strangest features in all of cosmology. The first she called the giant arc, a vast curve of galaxies and gas spanning more than 3 billion light-years, an enormous, gentle bow drawn across a region of the heavens. The second, found later in nearly the same part of the sky, she named the Big Ring, a near-perfect circle of matter, more than 1 billion light-years across, so large and so regular that it is difficult to imagine any ordinary process drawing it. Two colossal, almost geometric shapes, sitting side by side in the deep universe, each far larger than the principle says such things should grow. What makes these discoveries matter is not their size alone, but their challenge to that quiet, underlying assumption. If structures this large are genuinely out there, then the universe may not become smooth at the scales we thought. It may be lumpier, more organized, more full of grand architecture than the standard picture allows. And the equations that depend on uniformity would need, at the very least, to be revisited. It would connect, too, with those puzzling alignments in the ancient light. The faint sense that the cosmos has directions and features it should not have. And as always, there is the patient counter-argument, which may yet win. We are pattern-finding creatures, and the sky is vast, and in any large enough scatter of points, the human eye, and even careful statistics, will sometimes find arcs and rings and walls
that are not truly bound together at all. Chance alignments of unrelated things, dressed up by our hunger for structure. To know whether the Big Ring is a real object or a beautiful coincidence, we will need more data, more sky, more time. The question is genuinely open. But notice the shape of the whole story so far. At nearly every scale we have looked, the galaxies grown too soon, the black holes grown too large, the expansion rate that will not agree, the marks in the oldest light, the structures too big to fit. The universe has been quietly more surprising than our models predicted. None of it has broken physics. All of it has stretched our picture, pointing past the edge of what we currently understand. And the largest mystery of all is not any single one of these things. It is the simple, staggering fact of how much of the universe is missing, and how much of it lies forever beyond our reach. Here is a fact that took astronomers most of a century to accept, and that still, when you say it plainly, sounds almost like a mistake. Everything we have talked about tonight, the galaxies grown too soon, the cosmic web, the great walls, and the falling superclusters, all of it, every star and planet and cloud of glowing gas, is made of a kind of matter that accounts for only about 5% of what the universe contains. Everything you have ever seen or touched or been, all of it together, is a thin trace on top of something far larger and entirely unknown. The first hint came in the 1930s, when a sharp and difficult astronomer named Fritz Zwicky studied a great cluster of galaxies in the constellation Coma Berenices. He measured how fast the galaxies were moving, and found they were racing far too quickly to be held together by the gravity of everything he could see. The visible matter was not nearly enough.
Something invisible, something with mass but no light, had to be holding the cluster together. And he called it dark matter, and was largely ignored for decades. Confirmation came from the patient work of Vera Rubin, who in the 1970s measured how stars orbit within individual galaxies. By every expectation, stars far out at a galaxy's edge should move slowly, the way distant planets orbit the sun more slowly than near ones. Instead, she found them moving just as fast as the inner stars, as though held by far more gravity than the visible galaxy could provide. Galaxy after galaxy told the same story. They were each embedded in a vast, invisible halo of matter, far outweighing all their stars, shaping their every motion while giving off no light at all. We now believe that dark matter outweighs ordinary matter roughly 5-to-1, and that it forms the true skeleton of the cosmic web, the invisible scaffolding along which the glowing galaxies are strung. The faint ripples in the ancient light could never have grown into galaxies in the time available without this extra unseen gravity to pull them together faster. Dark matter is not a minor correction. It is the framework on which the visible universe is hung, and we still do not know what it is made of. That last point is worth sitting with. We have searched for the particle of dark matter for decades, in detectors buried deep underground to shield them from all other interference, watching for the faintest touch of one of these invisible particles passing through. We have built ever more sensitive experiments, ruled out candidate after candidate, and so far caught nothing definite at all. The most abundant matter in the universe streams through your body constantly, and through the whole Earth, and we have never once held it in our hands. The case for this invisible matter does not rest on starlight alone. In one famous collision of two great galaxy clusters, the visible gas was seen to lag behind, while the bulk of the gravity, traced by the way the wreck bent the light of galaxies lying far beyond it, sailed on ahead, exactly as it would if most of the mass were invisible matter passing cleanly through. To many, that collision is the closest thing we have to seeing dark matter directly. Others, unconvinced, have proposed instead that our law of gravity itself might need adjusting at the largest scales, an idea first floated by the physicist Mordechai Milgram. The debate is real and ongoing, and it is a healthy reminder that even our most confident numbers rest on assumptions we are still testing. And dark matter, strange as it is not even the larger mystery. Because when you add up all the matter, the visible and the dark together, you still account for barely a third of the universe. The remaining two-thirds, roughly 68% of everything that exists, is something else again, something even less understood, which we call dark energy. It is not matter at all. It is, as far as we can tell, a property of empty space itself, and it is pushing the universe apart. We learned of it suddenly in 1998, when two competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone expected it to be slowing. Gravity, after all, should be pulling everything back, gently applying the brakes to the cosmic expansion. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, studied the light of distant exploding stars to measure the expansion across cosmic time. And they found the opposite of what they were looking for. The expansion is not slowing, it is speeding up. Something is overpowering the collective gravity of all the matter in the universe and driving space to expand faster and faster. And it has been doing so for billions of years. The discovery was so unexpected and so well measured that it earned the Nobel Prize, and it rewrote the future of the cosmos in a single stroke. The universe will not slow, halt, and fall back together. It will grow and accelerate and spread its galaxies ever farther apart, driven by this pressure in the vacuum that we named without understanding. The simplest guess for what dark energy is would be the energy of empty space. The idea that the vacuum, even when you remove every particle, still holds a faint, constant energy that pushes outward. It is an elegant idea, and it fits the data reasonably well. But when physicists try to calculate how much energy the vacuum should hold, using our best theory of the very small, they get a number so enormously, absurdly larger than what we observe that the two cannot be reconciled by any ordinary means. The prediction misses reality by a factor with more than 100 zeros after it, often called the worst prediction in the history of physics. And the mystery may be deepening rather than resolving.
A vast recent survey called DESI, which has been mapping millions of galaxies to trace the history of the expansion in fine detail, has produced early hints that dark energy may not be perfectly constant after all, that its strength may have changed gently over cosmic time, weakening as the universe ages. If that result holds, and it is not yet certain, it would overturn the simplest picture entirely and tell us that the dominant ingredient of the universe is even stranger and more dynamic than we feared. Once again, the data is running ahead of the theory. So this is the universe we actually live in. A thin film of visible matter, ourselves, our world, every star, floating on a vast, unseen scaffold of dark matter. The whole thing carried apart on a tide of dark energy we cannot explain. 95% of everything is made of things we cannot name. We are a small, lit minority in a cosmos built mostly of the unknown, and we have only just begun to suspect how much there is still to learn. And nowhere is the strangeness of that emptiness clearer than in the great voids, the enormous regions where there is, very nearly, nothing at all. We have spoken of the cosmic web as a thing of threads and knots, of galaxies strung along glowing filaments. But the filaments are the exception. By far the greatest part of the universe, by sheer volume, is not the bright web at all. It is the spaces between, the voids, the immense dark bubbles around which the threads are draped, so large and so empty that the lit structures are really just the thin walls between one great emptiness and the next. The most famous of them was found in 1981, when the astronomer Robert Kirshner and his colleagues mapped a region of the sky in the direction of the constellation Boötes and discovered a hole in the universe. It is a roughly spherical region around 330 million light-years across, in which there are almost no galaxies at all. A stretch of space so vast that light needs hundreds of millions of years simply to cross it, and so empty that it became known, half in awe and half in unease, as the Great Nothing. To feel the scale of that emptiness, consider this. If our own Milky Way sat at the center of the Boötes void, we would not have known, for most of human history, that other galaxies even existed. The nearest ones would have been so impossibly far away that our telescopes might not have found them until well into the 20th century. We would have grown up believing our single galaxy was the whole of creation, alone in an apparently endless dark, simply because we happen to live in one of the universe's great hollow spaces. The voids are not perfectly empty, which is part of their melancholy beauty. Scattered thinly through them drift a few rare galaxies, isolated as nothing on Earth is isolated, with no close companions for tens of millions of light-years in any direction. There is one such galaxy that astronomers have informally called the loneliest galaxy in the universe, drifting in a void with no neighbors near enough to ever visit or be visited, evolving in a solitude so complete it is almost impossible to put into words. And those void galaxies, the rare ones, grow up differently. A galaxy in the crowded web is forever being tugged and disturbed and sometimes torn apart by its neighbors, its history shaped by collision and merger. A galaxy in a void has none of that. It drifts undisturbed, forming its stars slowly, gently, on its own unhurried schedule. A quiet life lived far from the turbulence of the bright regions. There are, it turns out, many ways to be a galaxy, and some of them are very lonely and very slow. Even our own corner of the cosmos sits beside one of these emptinesses. Just next to our local group lies a region called the local void, a large, underdense expanse, and part of the motion of our galaxy, that great 600-kilometer-per-second drift we spoke of, is the gentle push of this nearby emptiness sending us away from it. We live, in a sense, on the shore of a great nothing, being slowly nudged along its edge toward the denser, brighter regions far away. Our own emptiness may run deeper than the local void alone. Some astronomers have argued that the Milky Way sits within a far larger and shallower, underdense region, a great bubble perhaps 2 billion light-years across, in which galaxies are spread a little more thinly than the cosmic average. If we truly live inside such a hollow, it would mean our whole neighborhood is being gently drawn outward toward the denser walls around it, and that very pull might subtly inflate our local measurements of the expanding universe, offering one more possible thread in the tangle of that stubborn disagreement over how fast the cosmos is growing. Some astronomers have even wondered whether we might sit inside a larger underdense region than we realized. A great, shallow bubble of slightly below average density, many hundreds of millions of light-years across. If true, it could subtly affect the very measurements we make of the expanding universe, and might even play a quiet role in that stubborn disagreement over the expansion rate we followed earlier. The thought that our cosmic address could be tilting our view of the whole universe is a humbling one, and it is taken seriously, and it is not yet resolved. But I do not want to leave you with the voids as something cold or frightening, because to me they are the opposite. The emptiness is not the failure of the universe. It is the reason the lit places matter. In a cosmos that is overwhelmingly dark and overwhelmingly empty, the rare regions where matter gathered, where stars ignited, where worlds cooled and oceans formed, and something began to look back at the sky, those places are not the rule. They are the exceptions, vanishingly rare, almost impossibly precious. And you are sitting inside one of them right now. When you understand how much nothing there is, the something becomes a kind of miracle. Every galaxy is a lit candle in a cathedral of dark. Every star is a small warmth in an immensity of cold. And the fact that there is any structure at all, any light, any life, any awareness anywhere in all that emptiness is not a small thing to be lost in. It is the rarest and most beautiful feature of the whole vast architecture. And we belong to it, briefly, fully, here in one of the bright places between the great and silent voids. And yet, for all its vastness, even this, the web, the voids, the dark matter, the dark energy, everything we have mapped tonight, is only the part of the universe we are permitted to see. Beyond it lies a boundary we can never cross, not because we lack the means, but because of the deepest rules of the cosmos itself. To understand the true size of where we live, we have to come, at last, to the edge. The universe has an edge, but it is not the kind of edge you could ever sail up to and touch. There is no wall out there, no barrier, no final shore where the cosmos simply stops. The edge of the observable universe is a boundary made not of space, but of time and light. And understanding why is one of the strangest and most beautiful ideas in all of astronomy. The reason is simply that light is fast, but not infinitely fast, and the universe has only existed for a finite time. Light has had about 14 billion years to travel toward us since the beginning, and so we can only see objects whose light has had time to make the journey. Anything farther than that is not hidden by distance alone. Its light has not yet arrived, and may never arrive at all. The edge of what we can see is the edge of how far light has been able to travel in the age of the universe. We call it the cosmic horizon. But here the expanding universe plays a subtle trick. The objects whose ancient light is only now reaching us have not stayed still while that light traveled. Space itself has been swelling the whole time, carrying those objects ever farther away. So although their light took some 14 billion years to reach us, the galaxies that emitted it are now far more distant than that, around 46 billion light-years away, in every direction. The observable universe is a sphere some 93 billion light-years across, and we sit, as always, at its exact center. That centering is not vanity, and it is not special to us. Every observer, anywhere in the universe, sits at the center of their own sphere of visible light, bounded by their own horizon. A being in a distant galaxy would see a different sphere, overlapping ours, but reaching out to regions we can never see, and missing some that we can. There is no true center to the universe, and no true edge.
only countless overlapping horizons, each one the private boundary of a particular point of view. Your horizon is yours alone, and beyond every horizon, there is almost certainly more. The universe does not end where our sight ends. The careful measurements we have made of the geometry of space, testing whether it curves like a sphere or a sabble or lies perfectly flat, come back again and again, indistinguishable from flat. And a flat universe is consistent with one that is vastly larger than the part we can see, perhaps unimaginably larger, perhaps without any end at all. We may be living in an infinite cosmos and able to see only a single, finite bubble of it, like someone in a boat on a calm sea at night, lit by a single lantern, who can make out the water only as far as the light reaches, and no farther. There is no fear in that boundary, only a kind of vertigo, if you let yourself feel it. We are not at the center of something we can comprehend in full.
We are at the center of what we are permitted to perceive, surrounded on all sides by more universe than we will ever gather light from, separated from it not by any failing of our instruments, but by the deepest structure of space and time themselves. The unreachable is not a flaw in our knowledge. It is built into the shape of reality. It is worth being precise about which edge we mean, because there is more than one. One horizon marks the farthest light that has had time to reach us since the beginning, the boundary of everything we can currently see. Another, subtler one, marks the farthest any signal we send out today could ever travel before the accelerating expansion carries the rest forever beyond reach. The first horizon is about what we can know of the past. The second is about how much of the universe we could ever hope to touch in the future. Both are closing in their own way, and both are drawn not by any wall, but by the simple marriage of light's finite speed and space's endless growth. And if you find these long walks out to the edge of the knowable to be a comfort rather than a strain, if drifting toward sleep at the boundary of everything is something you would like to do again, you might let yourself follow this channel quietly, so that the next slow journey through the dark finds its way to you when you need it. There is no urgency in it, only an open invitation to come back to the edge whenever the night feels too loud. Now, there is one more thing about the horizon, and it is the most poignant fact I know in all of cosmology. Because dark energy is accelerating the expansion of the universe, the distant galaxies are not merely far away. They are being carried away from us faster and faster, and one by one, over the coming billions of years, they will be swept beyond our horizon and vanish from view forever. Their light will stretch and redden and dim until it fades entirely from the reach of any possible telescope. The observable universe, in the deepest future, will grow lonelier, not larger. Run that forward far enough, and the consequence becomes almost unbearable in its quiet. In the very distant future, every galaxy outside our own little gathering will have disappeared. Our Milky Way and Andromeda will long since have merged into a single great galaxy, and around it, the sky will be utterly empty. No other galaxies visible anywhere, no glow of distant structure, just one island of stars in an apparently endless dark. The rest of the universe will still be out there, but it will have receded beyond all possibility of being seen. And those far future astronomers, if any exist, looking out from that single galaxy into an empty sky, would have no way of knowing the truth. They could not see the expansion because there would be nothing left to watch receding. They could not find the ancient light of the beginning, stretched by then into nothing. They would have no evidence that there had ever been a Big Bang. no reason to suspect a universe full of galaxies, no path to the story we are able to tell tonight. They would conclude, reasonably, that their single galaxy was the whole of creation, alone in a static and eternal dark. Which means that we are living in a rare and privileged moment in the history of the cosmos. An epoch when the evidence is still visible, when the galaxies have not yet fled beyond the horizon, when the ancient light still arrives and the expansion can still be read. We can see the beginning because we are near enough to it in time. The light we gather is a gift of when we happen to exist, and it will not always be on offer. To be alive now, with the universe still legible around us, is an extraordinary stroke of cosmic timing, and it is one more reason to look while the looking is still possible. We have arrived, gently, at the strangest idea of the night, and I want to be careful with it, because it is so easily mistaken for fantasy. The notion that our universe might be only one among countless others is not a flight of imagination dreamed up for stories. It is a conclusion that some of our most serious physicists have been led to, reluctantly, by following our best theory of the beginning to its natural end. To see how, we have to return to the very first fraction of the first second. The ordinary picture of the Big Bang, for all its success, left two deep puzzles unanswered. The first was the uniformity we met earlier in the ancient light. The fact that opposite sides of the sky, regions so far apart they could never have touched or shared heat, nonetheless glow at almost exactly the same temperature. The second was the flatness of space, which appears tuned to an almost impossible precision, balanced on a knife's edge between curving inward and curving outward. Neither the smoothness nor the flatness had any explanation. They were simply how the universe happened to begin.
In 1980, a young physicist named Alan Guth proposed a single idea that resolved both at once. Suppose, he said, that in the first unimaginably brief instant, far less than a billionth of a second, the universe underwent a burst of staggeringly rapid expansion, doubling in size again and again and again, blowing up by an enormous factor almost instantly before settling into the calmer expansion we see today. He called it inflation, and it was one of those ideas that explains too much to be easily dismissed. Inflation solves the puzzles with a kind of elegance. If everything we can see grew from a single tiny patch that was smooth and in contact with itself before being stretched to enormous size, then of course the sky looks uniform. It all came from one small, even region. And if you take any curved surface and blow it up enormously, the part you can see becomes flat, the way the ground beneath your feet looks flat, though the earth is round. The smoothness and the flatness were not coincidences. They were the fingerprints of that first violent stretching. And inflation made predictions that could be tested. The same burst that smoothed the universe would have left a precise pattern of tiny ripples frozen into it, quantum flutters stretched to cosmic size, seeding the faint temperature variations in the ancient light. When the satellites mapped those variations in detail, the pattern matched what inflation predicted with remarkable accuracy. The search for the final proof of that first instant has had its heartbreaks. About a decade ago, one team announced that they had found it, a faint twist in the ancient light that inflation should have left behind, the very fingerprint of those first stretching moments. For a few weeks, it was hailed as one of the great discoveries of the age. Then a more careful look revealed that ordinary dust within our own galaxy could have produced the same twist, and the claim quietly dissolved. The true signal, if it is there at all, is still being hunted by telescopes at the bottom of the world,
and finding it would be among the most important confirmations in all of cosmology. It is not proven beyond all doubt, but it is supported well enough that most cosmologists take it as the best account we have of how the universe began. Here is where the other universes enter, and they enter almost against our will. Physicists like Andrei Linde and Alexander Vilenkin, working through the consequences of inflation, found that once this runaway expansion begins, it is extraordinarily difficult to switch off everywhere at the same time. In most versions of the theory, inflation ends in some regions, and each region where it ends becomes a calm, ordinary universe like our own. But in the spaces between, it simply keeps going, expanding faster than the pockets can form, forever spawning new ones. They called it eternal inflation. The picture it paints is vast, almost beyond comprehension. An endlessly inflating background, never stopping, and within it, bubble after bubble after bubble, where the inflation has halted and a universe has cooled into being. Each bubble a separate cosmos, complete and self-contained, expanding inside the larger frenzy, forever cut off from all the others by the ever-growing space between. Our universe, in this view, is one such bubble, not the whole of reality, a single calm pocket in an endless, churning sea of inflating space. And the bubbles need not be alike. In many modern theories, the laws that govern each universe, the strengths of the forces, the masses of the particles, the amount of that mysterious dark energy, are not fixed once and for all by some deep principle. They are set, more or less, by chance, in the moment each bubble forms, frozen in like the local weather of that particular cosmos. One bubble might have a stronger gravity, another a heavier electron, another no stable atoms at all. The physics we take as universal law might be merely the physics of our bubble, our local accident, one roll of the dice among endless rolls. Most of those other universes, if they exist, would be sterile and dark. Change the constants even slightly, and stars never form, or atoms never hold together, or matter never clumps into anything at all. A cosmos that expands and cools into permanent emptiness, with nothing in it to ever know it was there. Ours happens to have landed on the rare combination that allows stars and chemistry and structure and warmth, and eventually a creature lying in the dark, wondering about all of this. Whether that is luck or selection or something deeper is a question we will come to. There is even a faint, tantalizing way the idea might leave a trace we could find.
If, in the earliest instant, our bubble brushed against a neighboring one, the collision could have left a subtle mark, a circular bruise, a patch of slightly altered temperature, printed onto the ancient light. This is the source of that strange speculation we met earlier, that the cold spot in the constellation Eridanus might be the scar of a touch from another universe. Astronomers have searched the ancient sky carefully for such collision marks. So far, none has been confirmed. But the search itself tells you how seriously the idea is taken. What we cannot do, and will never do, is visit one. The other bubbles, if they are out there, lie beyond our horizon and are carried away by the inflating space faster than any signal could ever cross. We can reason toward them. We can find them implied by the same theory that explains our own sky. But we can never see them, never reach them, never hold any direct proof in our hands. The multiverse, if it is real, is the most profound thing imaginable that is also permanently, structurally, out of reach. And so we are left in a curious and humbling place, able to suspect, on solid theoretical grounds, that our entire universe is one bubble among countless others, each perhaps with its own laws, and yet forever unable to confirm it directly. It is the kind of idea that should be held gently, with neither certainty nor dismissal. But it is not the only map of the possible that serious people have drawn. There are other ways the cosmos might be far larger than it seems, and to see them, we have to turn from the universes that inflation makes to the still stranger landscapes that other theories imagine. If the idea of other universes were a single notion, it would be easier to hold. But it is really a family of ideas, arrived at from different directions, and the physicist Max Tegmark did the field a quiet service by sorting them into an order. 4 levels of multiverse, each one larger and stranger than the last, like a series of nested rooms, each opening onto a wider one. Walking through them slowly is one of the gentlest ways I know to feel the true size of the possible. The first level is almost modest and follows from something we have already said. If space is truly infinite, or even just vastly larger than the part we can see, then beyond our horizon lie endlessly many other regions, each as large as our own observable bubble, all governed by the very same laws of physics. They are not different universes in any exotic sense. They are simply the rest of our own universe, lying past the edge of sight, more of the same cosmos stretching on without end. But that simple idea has a dizzying consequence. In any single region of space, there are only so many ways that matter can be arranged, a number that is unimaginably vast, but still finite. And if space is infinite, with infinitely many regions, then every possible arrangement of matter must occur somewhere, and not just once, but infinitely often. Somewhere out there, far beyond any horizon, the particles may have fallen into precisely the same pattern as they have here. There could be a region identical to this one, down to the last detail, a copy of this world, this room, this moment, even of you, lying in the dark. Tegmark even worked out, very roughly, the staggering distance you would have to travel to reach your nearest duplicate. The second level is the one we have just explored, the bubble universes of eternal inflation, each frozen with its own physical constants, its own local laws. This is where the multiverse stops being merely more of the same and starts to include genuinely different cosmoses, some with stronger forces, some with heavier particles, most of them sterile, a rare few alive. And it connects to a strange feature of our deepest theories of matter, which suggest there may be an enormous number of possible sets of laws, a vast landscape of possibilities, often quoted as a number with hundreds of zeros, each one a different way a universe could be. The third level reaches down into the world of the very small, and it is perhaps the most disorienting of all. It comes from quantum mechanics, the theory that governs particles, which tells us that, before we look, a particle does not have a single, definite state, but exists in a blur of possibilities at once. The usual story says that when we measure it, the blur collapses to one outcome. But in 1957, a young physicist named Hugh Everett proposed something far more radical, that the blur never collapses at all. Instead, every possible outcome happens, each in its own branch of reality. The universe ceaselessly splitting into parallel versions, one for every way things could have gone. In Everett's picture, which we now call the many worlds interpretation, there is no single thread of events,
There is a constantly branching tree, and we experience only one path along it, while countless other versions of ourselves travel the other branches. Versions where the coin fell the other way, where a different word was spoken, where a small choice tipped the other direction. Tegmark argued that this third level, strange as it feels, does not really add new kinds of worlds beyond the first two. It is the same vast space of possibilities, realized in quantum branches rather than in distant regions of space. You might wonder, reasonably, why we never feel any of this branching, why experience seems so seamlessly single. The answer the theory offers is that the branches lose contact with one another almost instantly, as each possibility becomes entangled with its vast surroundings, and the separate paths cease to interfere. We do not feel the splitting, for much the same reason a river does not feel itself dividing around a stone. Each stream simply flows on, carrying a version of the world that no longer touches the other. Whether that is the literal truth of nature, or only a useful way of speaking, no experiment has yet been able to say. There is something quietly heartbreaking in Everett's own story, and it belongs in any honest telling of this. His idea was met, in his lifetime, with near total indifference. The great figures of physics dismissed it or ignored it, and he, discouraged, left academic physics behind and spent his career elsewhere, never seeing his work taken seriously. He died well before the tide turned. Only in the decades after his death did many worlds rise to become one of the most respected ways of understanding quantum reality, debated in the best departments in the world. He was right, or at least taken seriously as possibly right, and he lived and died believing he had been merely overlooked. The fourth and final level is the most abstract that anyone has dared to propose, and it is Tegmark's own. He suggests that every mathematical structure that can exist does exist, each as its own universe. That reality, at bottom, is mathematics, and that all possible consistent mathematical worlds are equally real, ours being simply the one we happen to inhabit. It is an idea at the very edge of what can be reasoned about, more philosophy than physics, and most scientists regard it as a step too far. But it sits there, at the end of the corridor, the widest room of all, where the question of what exists dissolves into the question of what is possible. If your mind is drifting now, following these nested rooms toward sleep, I'd gently say that this is exactly the kind of slow walk through the vast and the strange that this channel exists to offer, again and again on the nights you want it. If you'd like more of them, subscribing is the quiet way to let the next one find you. And then you can let the 4 levels go and simply rest in the feeling of how much larger reality might be than the single world we wake to each morning. What I want you to carry from all of these maps is not a belief. None of them is proven, and several may never be, but a loosening. For most of human history, we imagined a single small cosmos, a single sky, a single thread of events. Every honest map we have drawn in the last 100 years points the same way. Outward, toward more. More space past the horizon. More universes past our own. More branches past the one we travel. More possibility than we had ever let ourselves picture. Whether or not any particular map is true, the direction is unmistakable, and it is humbling. And it is somehow, when you sit with it long enough, a strange comfort. And there is one question that runs underneath all 4 levels, quiet and persistent, that we have circled without facing directly. Of all the ways a universe could be, why is ours one of the vanishingly rare ones that allows anything to exist in it at all? That allows stars and atoms and warmth and a creature capable of wondering why. That question has an answer, or at least the shape of one. And it leads us into the strange and beautiful problem of how finely the universe seems to have been tuned. There is a feature of our universe that, once you notice it, is very hard to stop thinking about. The laws of physics depend on a handful of numbers. The strengths of the forces, the masses of the particles, the amount of dark energy. And when you ask what would happen if those numbers were even slightly different, the answer, again and again, is that there would be no one to ask. The universe seems balanced with unnerving precision on exactly the narrow settings that allow complexity to exist at all. Consider the force that binds the cores of atoms together, the strong nuclear force. If it were just a few % weaker, the simplest heavy elements could not hold together, and the universe would be little more than hydrogen.
If it were a few % stronger, hydrogen itself would burn away too easily in the early universe, leaving no fuel for the long lives of stars. The force sits in a narrow window that allows both stable matter and slow-burning stars, and either edge of that window leads to a cosmos in which chemistry, and therefore life, is impossible. One of the most beautiful examples was found by the astronomer Fred Hoyle, who realized in the 1950s that the very existence of carbon depends on a delicate coincidence. For stars to forge carbon at all, a particular energy level inside the carbon nucleus has to sit at almost exactly the right value. And Hoyle predicted that this level must exist before anyone had measured it, simply because we are here, made of carbon, to ask the question. The level was found precisely where it had to be. Hoyle, who was not a religious man, admitted that the precision of it unsettled him and made the universe look less like an accident than he had expected. Consider the strange fact that there is any matter at all. In the first instant, matter and its mirror image, antimatter, should have been created in almost perfect balance. And almost perfect balance means almost total annihilation. Every particle meeting its opposite, both vanishing into light, leaving a universe of pure radiation and nothing else. But the balance was not quite perfect. For every billion pairs that annihilated, it seems, a single particle of matter was left over, unmatched. Everything that exists, every star, every world, every atom in your body, is built from that tiny surplus, the 1 part in a billion that had no partner to cancel it out. And consider the cosmological constant, the dark energy that drives the expansion, which we met as the worst prediction in the history of physics. The quiet horror and wonder of that mismatch is not just that our calculation is wrong. It is that for galaxies and stars to have formed at all, the actual value had to be almost incomprehensibly small. Small enough that the universe did not fly apart before gravity could gather anything together. The number appears tuned against the natural expectation to a precision of more than 100 decimal places. A little larger, and the cosmos would have expanded into cold emptiness before a single star was born. You can go on like this for a long time. The ratio between the strength of gravity and the strength of electromagnetism, the precise density of the early universe, balanced between collapsing back at once and dispersing too fast to clump. The number of dimensions of space, which only at 3 allows stable orbits and stable atoms. Each of these seems set within a narrow, life-permitting range, and the accumulation of them is what physicists mean when they speak, with a kind of uneasy wonder, of a fine-tuned universe. The question of why is one of the deepest we can ask, and there are essentially 3 honest answers, and reasonable people hold each of them. The first is simply that it is a brute fact, that the constants have the values they have for no reason at all, and that we should not be surprised by what merely is. This is logically unassailable and emotionally unsatisfying, and many find it hard to rest in. The second answer is that the fine-tuning points to purpose, that the universe so precisely arranged for the possibility of existence suggests, to some, an intention behind it, a meaning woven into the constants themselves. This is a reading that many thoughtful people across history have found compelling, and it lies largely beyond what physics can test or refute. It is not the place of an account like this one to settle a question that touches the deepest beliefs people hold. I only note that the precision is real, and that this is one of the long-standing ways human beings have responded to it. The third answer is the one that flows naturally from everything we have said tonight, and it is the multiverse. Suppose there really are countless universes, each with its own random settings of the constants. The inflationary bubbles, the vast landscape of possible laws. Then most of them are dead, expanded too fast, or never formed atoms, or burned out their fuel, sterile and empty and unobserved. Only a tiny fraction land on the rare combination that permits stars and chemistry and life. And in which kind of universe would any observer ever find themselves? Only in one of the rare living ones, because there is no one in the others to look. This is called the anthropic principle, named in the 1970s, and it turns the mystery inside out. The fine-tuning, it says, is not a coincidence requiring explanation, and not necessarily a sign of purpose. It is a selection effect. We find ourselves in a universe suited to life for the same reason a fish finds itself in water. Not because the ocean was made for the fish, but because a fish could not be found anywhere else. Out of endless universes with endless settings, the observers all wake up inevitably in the rare ones that allow observers. Our improbable good fortune is no longer improbable at all, once you remember how many failed universes we are not in. It is a powerful argument, and it is also a contested one, and honesty requires saying so. Its critics point out that a multiverse we can never observe is a heavy thing to invoke, and that explaining our universe by appealing to infinitely many we cannot see may be more a way of dissolving the question than of answering it. The debate is genuine and unresolved, and likely to remain so for a long time. But notice what it has done. The strongest reason many physicists take the multiverse seriously is precisely that it would explain why our single universe is so exquisitely suited to us. The fine-tuning and the other universes are two faces of one mystery. And so we arrive at a strange and beautiful suspicion that our universe may be one rare living bubble among countless dead ones, and that the very fact of our existence, the fact that there is anyone here to wonder at the precision of the constants, may be the deepest hint we have that the cosmos is larger than the part we can see. We are, perhaps, the universe's own evidence that it is not alone. But before we rest in that thought, there is one more frontier to cross, stranger even than the others. We have asked what lies beyond the edge of space. We have not yet asked what lies before the beginning of time. We have spent the night asking what lies beyond the edge of space. There is an even stranger question, one that sounds at first like a contradiction in terms, and yet some of the finest minds in physics take it entirely seriously. The question is, what came before the beginning? Whether the Big Bang was truly the first moment of everything, or whether time itself, like space, extends far past the boundary we can see. The standard story places the beginning about 14 billion years ago and treats that first instant as the edge of time, the point before which there was no before. But when physicists look closely at that first moment, the equations do something troubling. They predict a singularity, a point of infinite density, infinite heat, where the mathematics stops giving sensible answers and simply breaks down. And most physicists read a breakdown like that not as a real infinity in nature, but as a sign that our theory is incomplete, that something deeper takes over there, something we have not yet understood. Where the equations fail, the true story is still hidden. And so a number of serious proposals suggest that the beginning was not a beginning at all, but a transition, a doorway between something before and something after. The first of these comes from Roger Penrose, one of the great geometers of our age, who shared the Nobel Prize for proving that black holes are a genuine prediction of Einstein's gravity. In his later years, Penrose proposed an idea of startling strangeness, which he calls
conformal cyclic cosmology, and which imagines the universe as an endless succession of vast eras he names eons. His reasoning runs like this. Look to the extremely far future, not billions of years from now, but a span so long it dwarfs the present age of the cosmos. By then, every star will have burned out, all matter will have decayed, and even the great black holes will have slowly evaporated away into faint radiation, a process that takes almost unimaginable stretches of time. What remains is an empty, endlessly expanding universe filled with nothing but massless light, drifting on forever in the cold and the dark. Here Penrose makes his strange leap. In a universe with no mass left in it, he argues, there is no longer any way to measure size or distance or the passage of time. For it takes mass to build a clock or a ruler, and without it, big and small, early and late, lose their meaning. And a cold, smooth, scaleless sea of radiation in the infinite future, he claims, is geometrically indistinguishable from the hot, smooth, dense state at the birth of a universe. The end of one eon, stripped of all scale, becomes the fiery beginning of the next. Our Big Bang, in this view, was the remote future of a previous universe, and ours will one day become the dawn of another. Penrose has gone further still, and this is where most of his colleagues part ways with him.
With a collaborator, he has claimed to find faint patterns in the ancient light, gentle concentric rings, which he calls Hawking points, that he interprets as the echoes of giant black holes from the universe before ours, their final evaporations leaving a soft imprint that carried across the boundary into our eon. The claim is hotly disputed. Most cosmologists believe the rings are statistical accidents, the kind of pattern any random sky will contain. But Penrose, well into his 90s, has stood by it, and the search for echoes of a previous universe continues. A different path was taken by the physicist Lee Smolin, who proposed an idea both stranger and, in a way, more hopeful. Suppose, he said, that the singularity at the heart of every black hole is not an end, but a beginning. That inside each black hole, hidden from us forever behind its horizon, a new Big Bang occurs. A new universe is born. And suppose that each baby universe inherits the laws of its parent, but with slight variations, small mutations in the constants of physics, the way a child resembles its parents, but is never quite the same. If that were true, then universes would have something like heredity and something like offspring, and where there is variation and heredity, there is selection. Universes whose constants happen to produce many black holes would have many children. Those that produce few would have few. Over countless generations, the population of universes would drift toward the settings that make black holes most abundant. And here is the elegant twist. The same conditions that make black holes, long-lived stars, abundant carbon, rich chemistry, are very close to the conditions that make life. Our universe might be finely tuned not by chance or design, but by a slow cosmic descent, generation upon generation, toward fertility. Smolin called it cosmological natural selection, and it remains one of the most beautiful speculations in the field. There are gentler versions of the same instinct too. Some physicists, working with the quantum theory of gravity, find that the dreaded singularity may never actually be reached, that as the early universe is traced backward toward infinite density,
quantum effects intervene and bring the collapse to a halt, so that instead of a beginning, there is a bounce, a previous universe contracting down to a tiny, dense, but finite state, and then rebounding outward into the expansion we call our own. In this picture, the Big Bang was really a big bounce, the latest in perhaps an endless chain of contractions and expansions, a cosmos breathing slowly in and out across eternity. Other physicists have built cyclic universes of a quite different design. In one influential version, our cosmos is imagined as a vast sheet drifting in a hidden, higher dimension. And every great while, it draws into a neighboring sheet, the gentle collision releasing all the heat and energy we remember as a Big Bang. The two sheets then move apart and slowly approach again over almost endless stretches of time, colliding once more, so that what we call the beginning becomes merely the latest in an unbroken rhythm of contact and retreat, with no first touch and no last. And there is a gentler possibility still, proposed by Stephen Hawking together with James Hartle, which dissolves the question rather than answering it. In their picture, as you trace time backward toward the beginning, time itself gradually loses its sharpness and becomes more like another dimension of space, so that there is no first moment at all, no edge where everything abruptly starts. To ask what came before the Big Bang, Hawking liked to say, would then be a little like asking what lies south of the South Pole. There is no such place, not because the world ends there, but because the question, gently and completely, runs out of meaning. None of these ideas is confirmed, and I will not pretend otherwise. They are serious attempts by serious people to peer past the moment where our equations fail, and they disagree with one another, and the truth may be none of them. But they share a single, quiet suggestion that is worth carrying into sleep. That the beginning may not have been the beginning. That time, like space, may stretch far beyond the small lit stretch of it we can measure. That before the first light we can see, there may have been other light, other worlds, other beginnings, reaching back further than we can ever follow. If you have stayed with me this far, drifting at the very edge of time, then you already know the kind of company this channel keeps. The long, slow questions, held gently, with no need to resolve them tonight. If you would like more nights like this one, subscribing is how you ask the next journey to come find you.
And then you can release even this, the question of what came before, and let it rest unanswered in the dark, where the deepest questions are always most at home. Because we have now traveled as far out as thought can carry us, past the edge of space, past the edge of time, past our own universe, into the suspicion of countless others. And there is only one journey left to make tonight, and it is the most important of all. It is the journey back. Back through all of that immensity, all the way home, to the small, warm fact of you, lying here, made of all of it, belonging to all of it, at the quiet center of your own horizon. Let us come home slowly. We began the night with a patch of sky the size of a grain of sand, and a telescope 1,000,000 miles away gathering light for 2 weeks to see into it. And inside that nothing, we found galaxies grown too soon, and small red points no one could explain, and a single number that would not agree with itself. We followed the oldest light across the whole sky and found marks written into it that no one fully understands. We traced the cosmic web through its filaments and its great walls,
and its enormous, silent voids. We learned that almost everything is made of things we cannot name, and that the edge of what we can see is not a wall, but a horizon, slowly closing. And we let ourselves wonder whether our universe is one bubble among endless others, finely tuned, perhaps with something before it. That is a long way to travel in a single night. And notice what was true at every step of that journey. At every scale, in every direction, the universe turned out to be larger and stranger than our careful models had predicted. The early cosmos was brighter than it should have been. The expansion rate refused to settle. The structures grew too big. The missing matter outweighed the visible. The emptiness dwarfed the light. Again and again, reality ran ahead of the theory. And not once, in all of it, was there any cause for fear. Every surprise was an opening. Every mystery was the universe telling us, gently, that there is more here than we have understood. That is what the James Webb Telescope really gave us, beyond any single image. It showed us a universe that does not quite match any one story we have told about it. A universe that may be one of many, that may have had a before, that is mostly made of the unknown and mostly beyond our sight. It humbled our maps. And a humbled map is not a defeat. It is the beginning of a truer one. But here is the turn I want to leave you with, the thing worth carrying down into sleep. In all that immensity, the bubbles and the voids and the missing matter and the unreachable edge, you might expect to feel small and lost and far from home. And yet, the deepest fact of the whole story is the opposite. You are not separate from any of it. You are made of it. You belong to it as completely as anything can belong to anything. Consider where the atoms in your body came from. The hydrogen was forged in the first minutes after the beginning, in that hot, dense state we can still see glowing in the ancient light. The carbon in your cells, the oxygen in every breath, the iron in your blood, the calcium in your bones. Every one of those heavier atoms was made inside a star, cooked in the cores of suns that lived and died long before the Earth existed, and scattered across space when those stars came to their ends. You are, quite literally, assembled from the ash of dead stars. The universe we have been traveling through all night is not somewhere else. It is what you are made of. There is a thought the astronomer Carl Sagan was fond of, that we are a way for the universe to know itself. And the longer you sit with everything we have seen tonight, the less it sounds like poetry, and the more it sounds like plain description. The cosmos spent nearly 14 billion years assembling the atoms and the stars and the slow, patient chemistry and the long, unlikely chain of living things, until some small portion of it could lie here in the dark and look back at the light that made it. You are that portion. For a little while, in you, the universe has opened its eyes and is awake.
And there is something rarer still in you than starlight. Out of all that matter, the vast dark scaffolding, the endless empty voids, the countless sterile possibilities, a small portion of it here, in this rare lit place between the great nothings, has arranged itself into something that can look back. You are a piece of the cosmos that became able to gather 13 billion-year-old light and ask what it means. The universe, in you, has opened an eye. That is not a small thing to be lost within.
It is, as far as we know, one of the rarest things there is. You will never reach the edge of space, and you do not need to. You will never visit another universe, and that is no loss. You do not have to travel to what lies beyond in order to belong to it, because you are already a part of the single vast thing whose size you cannot measure and whose beginning you cannot find. The belonging was never in doubt. You were made by it and held within it from the very first. So let the questions stay open tonight. Let the early galaxies keep their mystery, and the number keep its disagreement, and the marks in the ancient light keep their secrets a while longer. Let the other universes remain unproven, and the something before remain unknown. None of it needs to be solved for you to rest. The light will keep arriving while you sleep, from the edge of everything, falling softly on a world that holds you. The universe will keep its mysteries warm, and they will still be here, patient and beautiful, whenever you wish to return to them. For now, there is nothing you need to understand, and nowhere you need to go. You are exactly where the whole long story was always heading. A piece of the cosmos at rest, in the dark, at the center of your own quiet horizon, belonging completely to something far too large to ever see the edge of. Let your breathing slow. Let the vastness hold you the way it always has. And sleep now, gently, here at the edge of what we can see, made of starlight, and far more at home than you ever knew.